Hello science fans! Today we're diving into the essentials of physics, work, energy, and power. In science, these words have precise meanings. Let's break them down. Work happens when a force moves an object over a distance, like pushing a box across the floor. If you push a wall and it doesn't move, no work is done, no matter how tired you get. It's all about force causing displacement. Energy is the ability to do work, the fuel that lets things move. You eat food for energy, which lets your muscles lift, run, or ride a bike. Energy comes in forms like kinetic, motion, and potential, stored. A moving car has kinetic energy, a book on a shelf has potential energy, ready to fall. Work and energy are two sides of the same coin. Work is the transfer of energy. When you lift a box, you do work against gravity, giving it potential energy. When it falls, gravity does work, turning potential into kinetic energy. Power is how fast you do work or use energy, the rate of energy transfer. If you and a friend push boxes the same distance but you finish faster, you're more powerful. Power equals work divided by time. That's why a rocket engine is powerful. It does a lot of work very quickly. Understanding these basics connects force, motion, and the energy that drives our universe. Now let's explore the work-energy theorem, a key principle in mechanics. It states, the net work done on an object equals its change in kinetic energy. Let's see how this works. Start with Newton's second law, F equals sine ma. Imagine a mass accelerating from velocity v to v over distance id. Using motion equations, we find vf2 equals sine vi2 plus 2 add. Rearranged, acceleration a equals sine vf2, vi2, 2 days. Work done, w equals sine fxd equals sine mxaxd. Substitute for a and simplify, w equals sine m vf2 vi2 slash 2. That's w equals sine 1/2 m vf2 1/2 m vi2. Since 1/2 mv2 is kinetic energy, net work equals the change in kinetic energy. For example, a pitcher's work on a baseball gives it kinetic energy to fly toward the batter. Let's talk about the forces behind work and energy. Forces are often grouped as conservative or non-conservative. Conservative forces like gravity do work that doesn't depend on the path taken, just the start and end points. These forces are linked to potential energy. Gravity gives us gravitational potential. Springs give us elastic potential. Work done by a conservative force equals the negative change in potential energy. In systems with only conservative forces, total mechanical energy stays constant. It just shifts between kinetic and potential. Non-conservative forces, like friction, depend on the path. Push a crate across a rough floor. The longer the path, the more work you do against friction. Energy lost to friction becomes heat, not stored as potential energy. Friction lets shoes grip the floor and cars grip the road. Air resistance slows parachutes. Most real-world motion involves both types of forces. Understanding the difference is crucial for analyzing motion. Conservative forces allow energy to be stored and recovered. Non-conservative forces dissipate energy, often as heat. Both shape how things move in our world. Let's put these physics ideas on the road. Your car's kinetic energy depends on the square of its speed. Double your speed, quadruple your kinetic energy. That means your engine must burn much more fuel to go faster. Air resistance, a non-conservative force, also increases with the square of speed. So, driving faster means fighting much more drag and burning more fuel. More fuel burned means more carbon dioxide released, a major greenhouse gas. Driving at moderate, steady speeds is far more efficient and eco-friendly. Understanding work and energy helps you save gas and reduce emissions. Physics isn't just theory, it shapes your daily choices. Smarter driving helps your wallet and the planet. All this energy and motion, it's powered by the sun. The sun, mostly hydrogen and helium, is a giant nuclear reactor. At its core, temperatures reach 15 million degrees Celsius. Here, nuclear fusion fuses hydrogen into helium, releasing energy. Einstein's E equals sine mc2 explains how a tiny bit of mass becomes a huge amount of energy. Energy created in the core travels outward, bouncing through the radiative zone for thousands of years. In the convective zone, hot plasma rises, cools, and sinks, bringing energy to the surface. From the photosphere, energy escapes as sunlight and heat. This sunlight powers life, weather, and nearly all energy on Earth. Every second, the sun fuses 600 million tons of hydrogen, converting 4 million tons to energy. The sun's steady output has sustained life for billions of years. It's our planet's most important energy source. Solar energy is the foundation of life, and a powerful resource for us. It's abundant and renewable. The sun gives Earth more energy in an hour than we use in a year. Solar panels generate electricity with no direct emissions, making solar power a key tool against climate change. Transitioning to solar reduces our carbon footprint and cleans up our air. But solar energy is intermittent. The sun doesn't shine at night or on cloudy days. To make solar reliable, we need storage solutions like batteries or thermal storage. Large solar farms require land and resources, and panel manufacturing uses energy and materials. While solar's impact is much less than fossil fuels, it's not zero. We must consider the full life cycle of solar technology. Still, solar is a sustainable path for our energy future. Harnessing the sun wisely can power a cleaner, healthier world. The challenge is making it reliable and accessible for all. Most renewable energy sources are just different ways of capturing the sun's power. Solar panels convert sunlight directly, but the sun also drives wind, water, and even biomass energy. Wind forms because the sun heats Earth unevenly, creating pressure differences and moving air. Wind turbines harness this solar-driven motion. Hydropower relies on the water cycle, which is powered by the sun's heat evaporating water. Rain falls, rivers flow, and dams capture this energy. Even biomass, burning plants or waste, stores solar energy captured by photosynthesis. Fossil fuels are ancient, concentrated solar energy from long-dead plants and animals. In almost every way, the sun is the ultimate source of energy on Earth. Renewable energy is really solar energy in disguise. Understanding this connection helps us appreciate the sun's role in powering our world. The sun is the original engine behind nearly every energy source we use. Harnessing it directly or indirectly is the future of clean energy. How do we capture the sun's energy? Two main ways: solar thermal and photovoltaics, PV. Solar thermal uses sunlight to generate heat, like rooftop panels that heat water. On a larger scale, concentrating solar power, CSP plants use mirrors to focus sunlight, creating steam to turn turbines and generate electricity. CSP is similar to coal or nuclear plants, but uses the sun instead of burning fuel. Photovoltaics or solar panels use semiconductor materials like silicon. Sunlight knocks electrons loose, creating an electric current. Many cells make a panel, many panels make an array, generating significant electricity. Both technologies face the challenge of intermittency. What happens when the sun isn't shining? CSP can store heat in molten salt, producing power even at night. Storage makes solar more reliable, bridging the gap until battery tech improves. Solar tech is evolving fast, making clean energy more accessible. The future is bright for solar innovation. Want to experience solar power firsthand? Build a simple solar device. A solar cooker is easy. Use a cardboard box, aluminum foil, black paper, and clear plastic. The foil reflects sunlight, the black paper absorbs heat, and the plastic traps it, enough to cook food or pasteurize water, or try a solar food dryer. A wooden frame, mesh, and clear cover let you dry fruits and veggies using only sunlight. These projects are great learning tools and help communities with limited access to electricity or clean fuel. Solar cookers reduce the need for wood or charcoal, cutting deforestation and indoor air pollution. Solar dryers help preserve food, reduce waste, and provide off-season nutrition and income. Building these devices teaches the science of solar energy and sparks innovation. Simple solar tech can make a real difference in people's lives. Science isn't just for labs, it's for everyone, everywhere. Try a project, share your results, and inspire others. With creativity and sunlight, we can build a brighter, more sustainable future. Go on, give solar a try.